So hereby I declare the examination open.
Honor Custer, honor opponent, ladies and gentlemen, my name is Tran Nguyen, and I'll be presenting my doctoral thesis on harnessing the physical properties of objects, robotic grasping and manipulation. So robotic grasping and manipulation has been studied for more than 30 years, and in recent decades, robots have been able to function well in control environment, like car assembly lines or production lines, where a robot repeatedly pick and place the well-defined objects millions of times. Nowadays, to deal with global challenge of the modern world, it is expected that the robot will be soon deployed outside industrial settings, for example, in home or in hospital, to assist human in our daily life. And in this new environment, robots are likely to interact with countless of complex objects, ranging from the complex tool like cutlery to deformable cloth or delicate food items. While substantial progress has been made toward this goal, the current method often relied on the assumptions about objects' physical properties, and two main assumptions that we observe are that objects have uniform assumed friction coefficients and objects are rigid. However, when it comes to more complex objects like multi-materials objects, where different parts of objects are made from different materials, or deformable objects, which are commonly encountered in our daily life, these assumptions do not hold. Therefore, these dissertations aim to go beyond this assumption by explicitly acquiring and harnessing the two crucial physical properties of objects, which are frictions and deformability in robotic grasping and manipulation. This enables robots to not only be able to see and recognize the objects, but also have a deeper understanding of the objects. We contributed to this goal with 6 following publications, and each of them will be mentioned later in the presentations. The first physical properties we tackle in my PhD is frictions. So why is frictions important for grasping and manipulations? So we grasp and manipulate numerous objects every day, and usually we succeed without any problems, but sometimes the objects slip out of our hand, and one of the most contributing factors to the failures is frictions. And that's why people invented a tool that makes from multi-materials, so the objects are still functional as they should, but also allow humans to have a more firm grasp on the objects. Therefore, I think it is extremely important for robots to be able to understand its properties and use the properties in the decision-making process. So to do that, we need to understand how humans estimate frictions. So humans often perceive frictions by visual and haptic cues. So to estimate a surface friction of an object, what we do is we interact with the objects by either sliding our finger across the objects and look at it. And through the feeling of the hand, we are able to distinguish between different surface properties or surface frictions. So how can we enable this ability on robots? We can achieve this by equipping robot with different sensing modalities. For example, a camera that look at the objects to give robot visual feedback, and a force sensor that measuring the force during the interactions to give robot haptic feedback. And with this setup, the goal is to develop a methodology that enable a robot to estimate frictions for all objects ranging from single materials objects to multi-materials objects. And our method is shown here. So first, what we need to do is we need to explore the object. So here, the camera will give the robot important information about geometry and colors of the objects, while with haptic exploration, you command the robot to slide its finger across the objects and measure the force. During the interaction, from the measured force, you can calculate the friction coefficients. So after this step, you will have the friction information, but only at this area where the finger had touched the objects, highlighted in red circle here. Then we need to have some models to estimate what would be the friction coefficients for the unexplored area of the objects. The approach is based on the idea that the similarity in colors will imply the similarity in friction coefficients. And for that, we learn the correlation between the colors and the friction coefficients from the data obtained in the previous steps. And then we use a regression model to infer the friction coefficients of the unexplored area of the objects together with the confidence in predictions. The result shows that the proposed method has successfully estimated the friction coefficients in the case of single materials objects. but also provide different friction coefficients for different part of objects that make from 2 materials or 3 or more materials. Here you can see the red color indicate the higher friction coefficients value. So we got the frictions information now. How can we make use of such information in robotic grasping? So in robotic grasping, a contact point between a finger and an object can be modeled with a friction cone. And this friction cone works in a way that if you apply force in the middle of the cone, it's better. And if you stay close to the edge of the cone, the contact point might breaks and the objects will slip. And this friction cone is defined by the friction coefficient mu, highlighted in red here. So the higher the friction coefficients, the bigger the cone, which means it's harder to slip. And for a 2-finger grasp, a good grasp is achieved if you apply the force inside both of the friction cone, as shown here. Right, so now we use that knowledge to plan graphs for a robot. And this is how the plan graphs looks like when we have absolutely no information about frictions of the objects. Here, what we can do is to assume the friction coefficients to be, for example, 1 across the surface of the objects. And therefore, the robot thinks that the graphs are equally good everywhere. And this is how the plan graphs looks like when we actually use the frictions information obtained with our method. So the plan graphs now only locate on the left side of the objects because the robot knows that this area has much higher friction coefficients to maximize the graph success rate. Now let's see some result. So we can see that all the graphs generated with planner that utilize the frictions information successfully grasp the objects because it's always aimed for the higher frictions area. While the graphs generated in case of no friction information sometimes fail to grasp the objects because sometimes it's aimed at the low friction area of the objects, producing slippage during the grasping and fail. So this result here again emphasizes for the fact that acquiring and harnessing objects frictions can lead to a higher grasp success rate that maximizes the performance of the task. The second properties we tackle in this PhD is deformability. And again, why is deformability important? As you can imagine here, it's really easy to crush or damage an object, deformable objects with rigid robotic hand. And therefore, we need to understand objects' deformability to adjust the force so we can still grasp the objects safely, but not crushing the objects. Another approach is that instead of using rigid robotic hand, can we just change to a soft robotic hand and forget about the object's deformability? So in one of our papers, we observed that even the soft hand equipped with force sensor and position sensor, it can still crush the objects if you apply too much force. So even in this case, you still need the information about objects deformability to regulate the force so you can grasp the object safely. One special thing about deformability is that instead of avoiding the deformation, we humans often make use of the deformation as well for various purposes. Like we usually deforming a sponge to clean the dishes easier, or deforming a clay to a desired shape while doing pottery. And our focus in my PhD lies in how to harness objects deformability in grasping and manipulation. So what are the problems with the current method? So as I mentioned before, the current method relied on the assumption that objects are rigid. So this method may not directly applicable for deformable objects. Some observation we have is that bad grasp on rigid objects does not mean it's bad for deformable objects, as shown in the figure here. Another thing is that the grasp planning method for rigid objects will eliminate many good grasps that exist only for deformable objects, like piercing into the sponge here and pinch the objects. So here the two questions arise. How do we quantify the quality of the same grasp candidate on objects with different stiffnesses? And then how do we choose where to plan a good grasp on objects with different stiffnesses to maximize the performance? Right, let's say we have, let's first address the first question. Says we have 3 grasp candidates as shown here on a deformable objects. Which one do you think is better than the other, and how would you know that? So in robotic grasping, we quantify the goodness of the grasp candidate with a grasp quality matrix. And this grasp quality matrix is just a numerical value that tells us the quality of the grasp. And it has been extensively studied for rigid objects, but not so much for deformable objects. So we decided to go beyond the state of the art by encoding objects deformability in graph quality metrics, so we can use it on a wider range of objects, including both rigid objects and deformable objects. So let's here consider the case where we try to grasp deformable objects with 2 fingers, and the red point here indicate for the contact location between the finger and the objects. As we increase the grasping force, the deformable objects will deform, and more contact point will form here, and this initial contact point might change. And this is how we see the robot sees things a little bit differently. You see the green shape here represent for the combination of all forces and torque applied to the objects by the finger. And different from the existing method, we continuously update this, and this is called graph strand space. So we continuously update this graph strand space based on the object's deformations. So you can see here as objects deform, we have much more contact. That's why we have much more bigger volume of the rand space here. Now let's try to imagine you try to disturb the objects by trying to pull it away in 2 different directions. And this is how it looks respectively in the rand space. So here, if we see on the right here, if the disturbance lies inside the rand space, we say that this graph is able to withstand the disturbance. So the graph is still good. However, if you look on the left, we see that disturbance penetrates the rand space, which means that it is able to break the graphs and steal the objects away. Therefore, this graph is not as good as the other one. So here what we can do is we can quantify the quality of graphs as how much disturbance a graph can withstand. And we can do that by fitting an enclosed sphere inside the rand space and use the diameter of this sphere as the quality metrics. And in short, the bigger the diameter, the higher the quality, and the better the graphs. We then quantified or compare our proposed quality metrics to 2 famous existing quality metrics, the Taylor for deformable objects as shown. And the results show that our method outperformed the existing method in performance. Here, our proposed quality metric is shown in blue, and it's linearly increased with the ground truth metric, while the other 2 do not. Also, it outperformed the existing method in terms of computational times, where it is up to 15 times faster to compute compared to the ground truth metric. So now we know how to quantify the quality of graphs on objects with different stiffnesses. Let's get to question 2, how do we plan good graphs for objects with different stiffnesses? So the problem setting is like this. So here we address the problem of generate good graphs on unknown objects with different stiffnesses lying on a table. So to achieve this, we incorporate objects deformation in the decision making of the robot. So we basically provide the information of the knowledge to the robot. And we do that by proposing a method that learns stiffness-dependent grasping strategy. And here we train a state-of-the-art neural network that take alongside the depth images of the objects, also stiffness of the objects. And we train this network in simulations, and the output would be the quality map where the red color indicate for a good place to grasp, and gripper width and gripper angle. The result shows that our approach is able to generate graphs on different areas of objects depending on the stiffness. Specifically, for example, on the top row, we see a soft sponge, and the robot knows the sponge is soft, so it allows us to grasp in more area compared to the case that the objects here is rigid. And here, for example, you can see the robot can actually peer inside the sponge and pinch it, while with the rigid sponge here, the robot only allowed the caging graphs, which mean caging the objects from outside. Then we run our method with the state-of-the-art neural network, state-of-the-art method on these 14 objects, which represent high variation in size, shape, and stiffnesses to test the capability of the method. And on average of all objects, our method outperformed the state-of-the-art GGCNN2, indicate in gray column here by 10% of higher graph success rate. And also it also demonstrates the importance of stiffness input here, because these first three columns, we use the same method, but in the blue here, we provide the method with correct stiffness input, while in the other two cases, we assume wrong information about the object stiffness. So here's some videos of a method in action. If we now change the stiffness of an object from low to high, you see the graph quality map change completely. It comes from very many areas to the lower part of the object itself. So it only restricts the graphs to be a specific place. The same thing applied for these objects. And here are some successful graphs with our method where with deformed objects, it can pinch inside and grasp, while with rigid object is still successful with the caging graphs. Right. So moving beyond grasping, we also investigate the potential of harnessing objects deformability in more complex manipulation task planning. So there are various manipulation tasks that involve deformed objects in the real world, like filling grocery bags, where the deformed objects here is the bag itself, or assisted dressing, where deformed objects here is the cloth, and dishwashing, again, where the deformed objects here is the sponge. And let's take a look at the dishwashing example. The deformability of this sponge allow it to conform to the curved surface. So if we apply the sponge here in this very edge, you see that the sponge will deform, and it allows the contact between both the wall and the bottom of the pan, so covering more areas. And this behavior of the deformable objects is really hard to predict, but it's very crucial for task planning. Therefore, we propose to learn a model to predict this behavior, taking into account the object's deformability. So here, the idea is giving an applied locations and the objects, and we know the stiffness of the objects, the model will predict the contact area between the deformable tool and the target objects here. Then we use this model to do planning, where we produce or we generate a trajectory to complete a task. For example, in this case, we consider the covering the whole surface of the objects, or this cleaning task. And we perform the experiment in the real world with these two objects. And the goal is to clean all the blue marker writing here from this object surface. And we see that although there are still some loose marker writing remains, the robot successfully removed above 90% of the blue marker writings on the target object surface. And here's the videos of our method in actions. Giving a plate, the robot will generate, or the method will generate a optimal trajectory so the robot can clean the objects. So in summary, in my PhD, I focus on relaxing prevailing assumptions that are constraining robotic grasping and manipulation. And I did so by proposing interactive perception method for acquiring and estimating objects' physical properties, and then take advantage of those physical properties and incorporate into a robotic decision-making process. I hope that my work will inspire roboticists to move beyond current assumptions and contribute to a future where robots can robustly and autonomously interact with more common but complex objects in the real world. This concludes my presentation, and I thank the audience for listening to the presentations. I would ask now Professor Roberto Calandra, appointed as opponent by School of Electrical Engineering, to present comments about my dissertation.
Thank you. My name is Roberto Calandra. I'm a professor at TU Dresden, and today it's my great pleasure to be here. I'm former alumni of this university, and I haven't been visiting the university in the last 10 years. So in addition to be a great pleasure to be here to evaluate the thesis of Tran, it's also a great pleasure to be here to be able to visit my former university. And I thank Professor Ville Kirki and again Tran for giving me this opportunity. Now, the reason why I accepted to be the opponent for this thesis is because of the importance of its topic, which is very connected and very interesting for me due to the closeness to the topics that I'm personally interested on. And just to give you some context of why this is such an important and interesting topic, for humans, it's very, very natural. It's very easy to be able to grasp objects, to manipulate in our hand without really even thinking about it. How do we do? What are the the informations that we're able to perceive this object while we are able to do this complex manipulation, in real time? And on the converse, for robots, this is an extremely challenging task. There are many different levels of complexity, from the sensing to the planning and the control, and eventually closing the loop and being able to do closed loop control compared to the current open loop approaches that most people uses. And there is this joke that in the robotic community that grasp has been solved for the last 50 years. There have been videos already from the 70s and 80s of Marvin Minsky being able to pick up cubes of metal from a table. And the common joke is that he already solved all of this for that one particular cube with that one particular material with that one particular friction coefficient. And what people have been doing in the last 50 years is just do the same in a way that we can now do this for all the remaining objects in the world, but that one particular cube. And what this really is aiming at is the fact that the work that Tran today presented is particularly important toward the goal of being able to generalize grasping and manipulation toward not only a single object, but any object that we might encounter into our everyday life, whether it's a hat, it's a pen, it's a cup or whatnot. And in order to be able to do this, we need to be able to better sense the world, understand it, and really be able to plan accordingly so that we can achieve this the same level of human dexterity and performance. So now I can see. Okay. So you have shown very impressive results and very impressive work today. My first question for you is, when it comes to the deformable object, which is an important topic, throughout your whole thesis, some people might argue that in order to deal with the deformable object, what you need to do is that you should just apply more force until the object completely deform, and at that point becomes a static object, and then you're done. You have solved the problem. So can you argue why do you think that being able to deal with really deformability and embrace it as you propose is important? And maybe give some examples of cases where we want to be able to do this rather than just.
Okay, sure. So it's true that I've been seeing the argument that you can just apply more forces, but as I presented, the special thing about deformable objects is you can do different things with it, either avoiding the deformation, because sometimes, for example, if you try to grasp let's say in the grocery shop, if you have a robot that's trying to put the stuff on the the shelf, and there you have the sample bottle, for example, you wouldn't want to spoil the content inside by applying too much force. From there you need to avoid the deformations, so apply how much forces you need to apply so that you can still put the objects safely in the shelf, but also not spilling the content outside. That's one thing. Another thing is we often using deformable objects, like with different various daily life, and we actually use the deformation, not just avoiding it. For example, like in the case of the sponge, you deform a sponge to a specific configuration that you feel comfortable to clean the dish. You don't deform it too much, so you have much less contact area, for example. Or in the case of assisted dressing, for example, you really need to understand the deformability of the cloth itself when you apply to some position of the human. So, and that's why I think understanding the deformability, the category of the deformable objects, and how do you make use of those for each of the purpose is important.
That's certainly a very valid point. Throughout your thesis, it seems that you took an approach where you want to analytically extract information in many cases about, for example, friction coefficient or deformability in a way that is interpretable for a human,
yeah,
which is sort of the traditional engineering approach that people in robotics have been taken throughout history. On the converse, recent development in learning, and in particular end-to-end learning, seem to suggest that you might not always necessarily need or to express these informations as clear, quantifiable numbers from first principles, but that you can in principle learn very complex network that somehow process this information internally without giving us this interpretability. Could you maybe comment on what do you think are advantages and disadvantages of these two potential approaches, and comment on why you chose to go down the path of interpretability and really having this explicit.
So in my opinion, why I go for the interpretability is that when you actually understand something, it's easier to modify than having to learn it implicitly. So for example, with the frictions, for example, we have been having different models that represent frictions like Coulomb frictions or Lucre frictions or many more frictions model. And the way I think of the problem is that I always utilize what it is now as state of the art and what is the easiest way to improve the performance using interpretability that human can actually understand. And how, because when we understand the frictions, for example, we know where to inject the informations, not just like having a neural network that learns something implicit that you couldn't be able to understand or it cannot explain easily. So that's one of the points. For example, in the DefGNN work, I utilized the state-of-the-art learning-based framework from one of the state-of-the-art method, and it learns to generate graphs from an image. So how can you raise the performance of that, having more the knowledge of the object? So that's why I inject again, my point is, if you know where what it is, you can easily inject it in different places to maximize the performance of the method, not just trying to learn it implicitly.
But do you think that both approaches, so in the long term, do you think that both approaches are potentially feasible, or if I should extrapolate what you're saying right now, your belief is that eventually we will always, the analytical methods will always be sort of superior?
Or well, no, not really. I mean, in my opinion, I would go for the hybrid approach where you actually incorporate the analytical, because we have been going through like 50 years of doing something analytical, and we need to make use of such information and then somehow combine it with the learning-based approach. So in my opinion, I will always go for hybrid way to do stuff, not just learning something or totally analytically doing something.
This is a great answer. I agree with you.
Yeah.
I think this is Related question. In your work about the quality metric, it could be argued that, especially if you are in support of this sort of end-to-end approach to to learning and manipulation, it could be argued that we don't really need metrics in the first place, and that the only metric that we might care about at the end is the empirical performance of how well is our system doing when we are grasping objects in the real world, hundreds of objects. So could you maybe argue a little bit more in details?
Sure.
About what do you think are is the importance of metric? Why should we learn metrics? How do you think that this will fit into the pipeline of other scientists also in the longer term?
Yeah. So the grasping learning has been shifting its paradigm from analytical, like sampling graphs and then check if the graph is good, to learning-based method where you learn a network to predict the graph's quality of a certain, or generate graphs from an image. And to do that, the learning method is often data hungry, and you need a lot of data to learn a good model that can generalize to more and more and more objects. And for those, you need to have a big data set. And even for state-of-the-art method like DexNet or GCNN2, they still need to train on a very large data set. And for those data set, they need to have some sort of metrics that quantify if the graphs is good or not. So that's why taking example in my work in the DefGNN, I learned that model by training everything in simulations. And the metric I use is that, okay, I have the simulation, I grasp the objects, I shift the objects around. If it drops, it fails. And it takes like 15 minutes just to evaluate one graphs candidate. And that's why that's why we come up with the analytical metrics, where you can just squeeze the objects a little bit, check if the quality is good, and it reduces much less time. For example, I just need 10 seconds now to evaluate a graph. And from there, if you think now it's exponentially grows, you can collect more and more and more data, bigger data set with the analytical metrics compared to the empirical metrics that I was using in the simulations. So that's one of the advantage, I think, having to use the metrics in the learning pipeline.
Let me go a little bit deeper, because I think this is a very interesting and important sort of topic.
Yeah.
For example, in other communities, like in the natural language processing community, people have been looking at metrics for decades, coming up with new metric. But in some sense, it turns out that, especially with recent development of ChatGPT and things like this, it turns out that all of these metrics were in some way useless, because the only metric that people actually cared at the end is how well does the system do with respect to a human that you have on the other side. And so my question would be, in the same way, couldn't we imagine in the case also of manipulation and grasping in particular here, think that maybe what we need is a human on the other side that tell us, yes, this is a good grasp, or no, this is not a good grasp. And if we deploy systems in the real world, let's say in the kitchen of people, eventually we want to make sure that the feedback of the users is what goes into, is used as a metric for learning, not so much some metric that might or might not be correlated with this real experience of people.
Yeah. So I mean, I agree with that. Having a human in the loop that decided the graphs is good or not is definitely better than any analytical metrics that we can think of, because analytical metrics based on physics, and I mean, there's assumptions and whatnot. So having humans in the loop always, because that's what we care about. I mean, in the end, we care if we successfully grasp the objects or not. So if you have a human in the loop, I agree, it's better. But Having a robot or a suitable metric or reasonable metrics to in simulation, for example, it saves a lot of times. You can, I mean, you can quantify millions of graphs in the order of minutes. But having a human there, it takes like months to, okay, yes, this is good. No, this is good. So to achieve the same amount of graphs, I think with human in the loop is better. Of course, it's raise the performance, but the drawback would be the times consumed there to collect the amount of same data.
In your publication, you showed the monotonicity of your metric with respect to other metric.
Yes.
Which is very important because it basically shows that it should be more correlated with the graph success. But even in that case, it was only evaluated on 5 objects, and it was on the success rate of the grasping, but not necessarily on the quality of the grasping. Again, that a human could somehow measure. Can you imagine, sort of for people that will be working on this field in the future, how can we fill even more the gap between having metrics that seems to be correlated toward more human-like metrics? What do you think is the next natural step that we could do that?
It's a tough question. I mean, what comes to mind right now is to have a human as the oracle to, it's like learning from demonstration, for example, having a human as the oracle to justify if this is good or this is bad. Besides that, I don't think there will be any system that is good enough. For example, a simulator or anything would be good enough to quantify the quality of a graphs better than human, I would say. It all comes down to, if you want to have a very accurate quality, then you include human in the loop. If you want to learn a generalizable method with a huge bunch of data, then you can use a reasonable metrics to generate a huge amount of data.
Another very interesting point that you mentioned when talking about quality metrics is the speed of the simulator. And so you suggested that having good quality metrics is a way, in some way, to speed up the training, the data collection. This also seems to hint at a more deep problem, which is the fact that simulators might be slow, the fact that collecting real data also might be slow. So specifically about simulators, and we will go back to the real world later on. Can you comment on what is your opinion about the state of the art of current simulators? So, and why can't we simulate millions of grasp perfectly in a second? What's the issue there?
Yeah. So, okay. So simulator is an approximation of the real world always. So if you are approximating something, it means that you can always fall into some local minimum that fails, for example. And the current state of the art for simulator, I think for rigid objects, for example, because the shape doesn't change when you apply force, it's much easier to simulate than the deformable objects. Let's say we have GraphSpeed that can generate millions of graphs in the order of minutes, but for deformable objects or soft objects, it has to went through the simulating the deformable or the deformability behavior of the object first, and then continue with the process. And simulating deformable is not easy. Nowadays, there are plenty of simulators. For example, Isaac Jim is what I'm using, PyBullet, PyFlex, whatever. But still, it's far away from what it is in the real world, because in simulator they use different, let's say, representation for deformable objects, like either using FEM, finite element method, or using mass spring damper, again, as an approximation system of the object. So it takes time to simulate those things. So it's really slow to simulate some deformable objects. And that's why I said that with the ground truth metric I use in the quality paper, it takes 15 minutes to evaluate a graph. Because if you increase the complexity of the objects, like have bigger objects or denser elements in each object, it takes way more times. Each element required, let's say, 2 seconds. So if you have 1,000 of it, it increase, and that has to be done because you need some model to predict the behavior of the deformable object.
For the larger audience, can you just detail a little bit more into details how, for example, a FEM model works and how is it solved?
So okay, I'm not an expert on mechanical, but I can try to explain some part of it. So imagine you have an object like the bottle of water, and you will try to predict the behavior when you do this kind of grasping. And the FEM method is that instead of learning a continuous function for the whole object, you discretize the object into smaller elements. So basically, you divide this object into 20,000 of small, let's say, rectangle or anything here, and then you try to solve the numerical approximation in each of those elements, which is easier and easier to compute compared to a continuous function. So that's what FEM do. And since it tried to solve 20,000 of numerical function on each element, that's why it takes so much time as well. It comes with the accurate, the more you discretize the objects, the better, but it also comes with the computational times required for computing all of them. So that's the drawback of FEM.
Absolutely. This is a widely acknowledged and accepted problem, I think, from everybody working in robotics, that we don't have the necessary and right mathematical tools. And even with the access to massive computation like GPUs, it's still very slow for what would be desirable. Can you comment on the ease of use of current robotic simulators?
You mean each of use, or
how easy it is to use and program?
I actually have a lot to comment on that because I've been spending months to get a simulation running, yet creating an environment for it to be like usable. So I mean, it's not easy to use. It's relatively new, so people is still researching how to do good simulators that provide soft body simulation, for example. The reason why I use Isaac Gym is it is not easy to use, but it's easier to use compared to others. So that's one thing. And what else? I mean, because it's new, so there's no much documentation, so it's really hard to get someone to start and use it directly. So what I would hopefully inspire or comments for a future work on that is, if you have something that worked, try to make a documentation out of it. So for example, in my environment, I try to make some documentation so others can jump into that, modify what they need and use it directly. Because sometimes what you need is not exactly the environment, but you need that back end to create some environment to yourself and train some sort of policy. So
from your word, it seems that using modern robotic simulators is almost a black art that requires black knowledge that might or might not be hidden and passed from student to student. So just maybe also for the audience to understand, can you quantify how many hours would take you to set up robotic simulators?
I mean, it depends on the simulator itself, right? But for example, I can talk about Isaac Gym. Now, if I start from scratch, it will take me 25 hours, let's say. So a daily work is 8 hours, right? So I mean, for all PhD is like 20 hours. So I would say, I mean, you need 3 normal days to get it working, smoothly. It's around 24 hours, I would say, for good documentation simulators. For example, I tried to use Omniverse, NVIDIA Omniverse, which contains Isaac Gym and whatnot. I spent a week and I couldn't get it run. So I have to ask from my college to help me with that. And it, again, takes 2 days to understand it. And I mean, 2 more days to develop something. So it takes time.
Thank you for your insights. So going a little bit back into your second and third work about the deformability, but remaining on the topic of sort of infrastructure for science. In section 3.2.2 of your thesis, you mentioned the fact that you collected about 27,000 graphs for training your model. However, by modern large-scale training of complex models, 27,000 is a relatively small number. Larger models, neural network models, can require millions or even billions of data. So I wanted to know, first of all, why did you decide this number 27,000, or how did it happen to be?
Yeah. So as I mentioned earlier, so in this work, I still use the ground truth metric coming from the simulators, where I actually interact with the objects, moving it around. So it takes like 15 minutes for one graphs candidate, and that's one of the reasons why I can't generate more in that short-term span. I spent like months to collect those 20,000 graphs, and I know that the number is small, but that's why I try to do some sort of data and augmentation by rotating, zoom and crop, just to help some more, just to have some more data points. But I mean, that 20,000 graphs already cost me like 3 months to collect the data. It takes some time. Yeah. So that's why I stopped at that number.
So we can say that this was constrained by real-time constraint of time.
Yeah.
Able to drive your research within reasonable time
Yes.
frames. However, I would be very interested in knowing, given that we have in practice this constraint in the real world, whether we work in simulator or whether we work in with data that we collect from real robots. How do we control for the fact that the behaviors that we are learning, or the models that we are learning, might in practice be underfitting or overfitting? How do you control that the models are actually trained to the right place, and the complexity of basically the amount of data that we have is sufficient?
So it's really hard to say. You can actually control that. Like, you have a number in mind how many graphs that you need to train a good model. So what I would do usually is I train a model with a certain number of graphs or data points, and then I go to the real world and test with the objects that are outside of the training data set. So if it worked for those objects like 100%, then you can be more confident that your model is able to generalize outside of training set. However, if you put like two new novel objects that are totally different from what you have in training data, and it doesn't work, it means your model is overfitting, and the easiest way is to have more data, more model regarding that shape of objects or something. So I mean, I would do trial and error or evaluating in the real world to know that our model is capable of generalization or not. So that's what I would do to, I mean, in a way, control the model.
What do you? Why not using, let's say, validation and test sets?
And I mean, that's also use already in the simulation phase. So when training something, I always have this validation set and test set. But I mean, in the real world, we have much more complex objects, or I mean, different stuff, different objects in the real world. I mean, that's the core thing. When you train something, you always have to have validation and test. So you can somewhat quantify the generalization capability already in simulation.
And do you have any intuition of since this 27,000 is just a data point, basically in a data regime that may vary depending on how much time you have. And since training your model is relatively cheap compared to acquiring the data, have you thought about performing an ablation study of how the model performance changes with respect to the number of data that you have?
Yeah.
Because this might motivate, maybe if we see that we are still growing very fast in terms of performance, we might decide to wait 1 more month to collect more data. Or on the other side, we might say, okay, for the last 10,000 data points have been at the same performance, the system is already sort of at regime, we don't need to collect more data.
I agree that an ablation study is well needed to quantify like if your model is good enough. Unfortunately, I didn't do it in my work. That's one of the reviews I got from the reviewers actually. But in the end, I didn't do it. But I agree that, I mean, having an ablation study definitely helps.
Thank you. Continuing on paper 3, I should talking about paper 3, but also to a more general statement that you have initially in your thesis in section 1.2. You basically suggest the fact that providing data sets is a great value to the community, which is something that I fully heartedly agree. I think this is very, very important. This is something that can really have a deep impact on, being able to have synergies across different institutions, across different research labs. And we have recently seen some amazing work also from some of these very large consortiums, 30 universities, consortium data sets. However, I wanted, first of all, to point out the fact that when clicking on the link that is included in the thesis and in the paper, this link is currently not accessible. And therefore, I wasn't able to really get information of how much these data sets that we've been publishing have actually been impactful for other scientists. So I basically wanted to ask you if you know of other researchers that have been using the data set that you've published to build on top of this. And this would, of course, confirm and strengthen even more the conviction that publishing data set is important, and this is a great impact of your work.
Yeah. So I'm sorry that the link doesn't work. Probably, I mean, I checked it when I submitted the paper, so we will fix that for sure. About the people using our code, I have to say that there is one, at least I know, used the data set from the grasping, the grasp quality metric paper. The people from NVIDIA actually who developed the simulator, they used it to, I think in one of their work that used differentiable model to quantify the grasp. So, and they cited our paper and they used the data set because the author contacted me for that. So I'm sure that they used that. And I think we have a couple of requests from the frictions paper as well, because I mean, for some reason they wanted to have more objects, more frictions. So I would say that there's people using the data set, so they're definitely helpful there. Yeah. So that I can confirm.
That's great. I've personally been gone through the pain of open sourcing data sets. There are handful of them in the whole manipulation grasping community. They are very rare. It's a gigantic pain to publish them, but I think it's really important, and I want this to be recognized. It's actually a very valuable effort.
I mean, one comment I can make from here is the data set that developed from in the DefGNN paper is based on a very famous data set. It's Cornell data set. So the way I built my data set is, I mean, try to develop on what they have. So if people want to incorporate it, it's easier, so they don't have to have two different data sets. So I mean,
I assume you would need to generate the data of the deformability.
yeah, I mean that you need.
Moving on to the section 2.3.1, which is about the friction estimate. I'm very curious about what type of tactile, or how you call them, haptic informations you are collecting from your tool. And this is a more, I would say, general question about, which I think nobody knows, but I would be very interested in knowing your answer, about what are the type of haptic informations that we actually need. And to give more context to the audience, touch is a very, very important sense modality in humans. We don't really understand in our everyday life or appreciate how important it is, but there have been many studies showing that without touch, people actually fail to do very simple tasks, even lifting objects or lighting a match. It becomes extremely difficult. However, a fundamental question which is open at the moment is, what are the actual informations that we are gathering from touch that we are using? And the problem is the fact that our skin is made of many different types of mechanoreceptors, which can sense basically everything from temperature to vibrations, high frequency vibration, low frequency vibrations, forces, deformations, pain. And of course, the sensors that we have at the moment and the experimental setup that you use in your work only capture a part of it, but it might be still very valuable toward the goal of understanding what parts of this tactile or haptic informations is used in which particular case or for what particular scope. So going back to the beginning of my monologue, I basically will ask you again, what type of tactile informations or haptic informations were you collecting? And if you can comment what type of haptic information you think we would need in order to do better with the friction.
Okay, so specifically in this work, the haptic information I collect is just the measure of force from the force and torque sensor. So basically you slide along the object, you measure the normal force and the tangential force acting on the finger. So that is what I use, especially in this paper. The main reason is that because the goal of the papers is to estimate friction coefficients, and those value is what needed to compute that specific value. So that's why I use that tools there. However, as you say, touch is important and it's very complex. Even for human, like I usually go around poking at picking stuff and feeling it. So what I feel is, of course, the force that is applied at my hand or my finger, where is the pressure applied in my finger. And it's very amazed me that even without looking at it, we can still feel how our fingers deform and what are we holding here and what is the orientation of the pen. So I would say for different purpose, you would need different haptic information. For example, in one of your work is in-hand manipulations. There you have a vision-based tactile sensor, right? So you can capture basically the deformation of the sensor to estimate what is the shape of the object. And from there you can easily do, or not easily, but you can do this kind of in-hand manipulations. So that is one thing I think that is important as well. Another type of haptic is like where did you touch the objects, where in the finger you actually, so imagine you discretize your finger into different patch, and then you apply you press an object, and the information there would be the pressure applied at different areas of that fingers, and that's also one type of information. So I mean, in short, that is measuring force, the pressure, and with the vision base, maybe you can have this kind of deformation in the sensor that gives you the opportunity to see, or to see the objects to some extent in the sensors.
Thank you. I think this is certainly a good answer. In the case of your experimental setup, though, you said that you're measuring, forces. However, you are also applying forces because you are controlling eventually the tool as it slides through the surface. So my hypothesis that I would like you to comment is that maybe the type of features or sensing that you actually are having is maybe not so relevant in terms of forces itself, but maybe what you're arriving at is maybe something more similar to vibrations, or maybe even the roughness of the object. Do you have any intuition whether this might be true or not?
Okay.
Or
So
if you have given any thought?
when I did the literature reviews, and there's been plenty of work that doing the same thing, haptic explorations to estimate the frictions on an object. I mean, one noticed they usually just assume the object is uniform, so you just slide the objects there. So there's different work that either calculate the frictions coefficient directly, or use some kind of even more low-level processing to go to the vibration space, and from there you can distinguish different surface from each other, because if you have rough surface, the vibration goes like a bazaar, and if you have smooth, it is normal. So there's definitely if we want to go to that deep, we can easily distinguish different materials from each other. But in my case, I think the main point is to have a knowledge about what object is not made of, but like what is the area that has higher friction than the other. Because in the end, the downstream task in my case is grasping. So I care about if this part and that part have the same frictions or not. So maybe the use of the friction haptics information in my case is a bit naive, but it served the purpose of what is the downstream task needs in my case.
I'm just suggesting the fact that although you're measuring forces, it's likely that indirectly you are actually measuring informations like vibrations or roughness.
I agree.
Because these are much more closely correlated with friction. So it would be very interesting to look into the model of what you're learning and try to see basically what can be, how it can be interpreted. Also, still in section 2.3.1, your model is basically using both vision and touch, and I would like you to comment on the relative importance of these modalities. Sure, we can start from here.
Okay, so with the vision, you can get the geometry of the objects and the visual features of the objects, like colors, curve, and whatnot. with the haptic exploration, what you can get is the measure force. So it's like interacting with the objects blindly. So you don't see the objects, but you know what you are in contact with. So that's why I use these two combinations, so that I can still get the contact interactions to calculate what is the frictions. But also I look at the objects so that I can then later, infer or guess. It's like human. We slide just one slide, but then we can look at the object and say, oh, this is the same color as this, so maybe it has the same frictions. So that's based on the intuitions from the human.
So do you see them as complementary?
They are complementary to
Right.
each other.
How about so I generally agree with this view that they are complementary. However, there are also evidence from, for example, neuroscience, that another way of interpreting these two modalities is in a kind of loosely speaking Bayesian way, where vision might provide you a prior over information, and touch might then give you evidence to compute your posterior and update your prior. However, in your model, it seems that both modalities are basically used at the same time, sort of in the same way. Can you imagine some variation of your model that can more closely mimic how this type of framework of prior and posterior?
So I actually have the same idea you did after the work. So there are works that try to estimate the frictions from vision only. So look at the objects and then giving a prior of what it is, what would be the frictions. I think even in that case, the haptic is still important, because if you have an object made from different visual feature, different colors, and you try to guess that, you will have different frictions for each of the colors, I would say. Or now you have the fake wall, wood painting or whatever, but it looks like wood, but it's not wood. So that's where the haptic comes in play. And I agree that there would be nice if we have a variation that look at the objects, give the prior of the friction, and then update the posterior based on the haptic informations we collected. So that would be a really nice variation.
And I would also add the fact that since some material might have not only colors but textures might also be a very important confounding factor for a vision-only system, because different textures might be misleading the model in thinking that there are maybe different friction coefficients, although that's just patterns of the colors. However, continuing this line of thinking, could you imagine some experiments based on your existing work, where basically to understand better how important each one of these two modalities is? So just to give an example, would it be possible with your existing model to mask one of the sensing modality entirely, the input, and look at what performance the model would have, or mask remove vision or remove touch and see how the performance would behave?
I would say if we talk about my model, I say if we remove the vision, what we can get in the end is just frictions coefficients. So in the end, you will have a line of exploration, and then okay, this part have a higher friction, this part has low friction. So I mean, you just have that information if you remove the visions. And I mean, in my work, if you remove the haptic, then there's nothing. So yeah, unfortunately, my work, you can't really mask out anything, because it wouldn't give you anything as sufficient. I mean, you can remove vision, but at the end, you don't have that much information you want. Yeah, but in the case of another variation that you talk about, if we remove the haptic, we still have some prior. May be true, that may not be true. So you still have something, but in my case, if you remove one of them, you still have something, but nothing.
Perfect, thank you. So I really liked, as a general theme throughout the thesis, and in particular in section 3.1.1, that you point out this distinction between minimizing and harnessing deformation. I think that this is a very important point. It's also very much a point that is overlooked by many people in the community. So I would like you to tell me more a little bit, what do you think that harnessing this deformation might lead us, in, let's say, 10 years, 20 years down the line? What are the tasks that you think that we really need to harness the deformation before we are able to achieve it, and that we will never be able to achieve it without? If you have some, if you agree on any thought about this.
Yeah. So about minimizing and harnessing, I have to give compliments for Ville as well, because we propose those together while looking at different example in the real world. And I think one immediate example comes to my mind when you need to understand the object deformation is probably maybe in assisted dressing, where you need to really know the cloth, how cloth deform, and you have to be aware of that to be able to assist dressing, or even in cloth folding, you need to have the awareness how objects will merely deform or behave when you applied something. So I think in those cases, harnessing deformability is always helps in the planning aspect, please, because I mean usually in robotics we have planning and act, the open loop, but plan and act. So this harnessing or having the awareness of the object's deformability is really important in planning phase, and also that is highlighted in the 5th section here with the sponge work. So you have an awareness that the sponge is soft and how it would deform, like when it is interacted with the rigid bodies, and then you take those information into account while doing planning.
Now, I think this is a great answer, but going back, and this is a point that I already asked you, but I will ask again from a slightly different points of view. In your work, since you are extracting analytical informations like friction and deformability, you're then constrained, if one would argue that this is a limit, you're then constrained to do traditional control and planning to basically integrate these informations to make use of this information for control for robots. Can you imagine what other paradigm you can use instead of using traditional analytical planning to use these informations for eventually controlling robots?
Okay.
Could you, for example, imagine that this information that you're extracting are sort of a sensing module, and then you can learn a controller on top of that?
Yes. So maybe if we think in terms of model-based reinforcement learning, for example, where you try to learn some sort of model that predicts something, or the model of the deformable object itself and how it deforms under interactions. From there, it is easier to learn and easier to generalize to different tasks with the next like module like area or something. So I think there are worked on, I mean, again, a cloth deformable objects manipulation that do model-based reinforcement learning, where they first try to learn some model that predicts the dynamics of the objects, and then use that model for planning, not just traditional planning method.
And do you think that this will be a future promising direction?
I would say so. Again, it's hybrid approach. You have some model that predicts something about the world, and then you use that for learning. Is better, in my opinion, and it is easier to generalize for more tasks, in my opinion, rather than learning model-free RL, where you're trying to learn maximize the reward for one task only, and then you move to another task, then you have to learn it from scratch. I mean, not an expert, but at least that's my view.
I think you just opened a can of worms. Let me just very kindly scratch this.
Yes.
Why do you think? Can you describe what are the advantages and disadvantages of model-free versus model-based reinforcement?
I mean, again, I'm not an expert on RL, so it's just coming from a naive perspective. But I mean, for model-free, you can learn a policy to perform a task that maximize some sort of reward. But for model-based, you have some sort of model of the world. I'm talking about deformable objects manipulation, for example, and you have a model that can roughly predict how the objects will deform under interactions, and you can use it for learning. So one of the drawbacks that I might think about the model base is that instead of having one source of error, you now have two, because you have to learn the model and then use the model to learn the policy. So in that sense, maybe you have more computational cost and also the more uncertainty or source of error. While with the model-free RL, you try to learn a policy, maximize the reward. So you have one source of error over there. But I mean, again, naively talk about RL, if we have some sort of model about the world and you trying to solve two similar but not the same task, maybe you can make use something out of it with the model base, in my opinion.
Yeah, I think it's questions besides the scope of the thesis, so I'm not got too much there. But for the general audience, model-free, there are proponents of model-free approaches that would argue that with the right training process and with domain randomization and other approaches, you could in principle be able to generalize to objects also beyond your training distribution. So it's an open questions, and there are philosophical conflicts in the community of this topic. Okay, thank you very much. That's the answer.
No, thank you.
I would like to now move a little bit more toward the last chapter of your thesis, and I would like to pick your brain or know your opinion on soft robots versus tactile sensing. And the context of this question is that it seems that except very rare exceptions, there seem to be two opposing again communities where of how to deal with the deformability, of how to deal with compliances of objects in the real world for manipulation. And one of these parties are supportive of the idea of soft robotics, where the deformability of the world is somehow managed at the level of the hardware, where you design smart hardware that is capable of adapting and deforming. You're basically taking away complexity through a smart design of your hardware, so that your control can then become very, very simple. And on the other side, there is another part of the community that would argue that what you really want instead to have is that you want to have better sensing, and specifically better tactile sensing, so that you are able to sense these deformations, but then you want to be able to control them by having maybe more complex controllers, but that also give you the freedom at running time to decide what to do, rather than having a hardware which is basically only capable of doing one single type of actions. So can you describe where your work fits inside, between these two fronts, and sort of what are your thoughts on this?
So when about my soft hand work,
Yes.
that's actually my very first work when I joined this group as a master thesis student. And there, I mean, back then the soft robotic just start to grow, and there's nothing much more than a few robotic hand design. And I think we barely start to learn about it. But in my opinion, about soft robotic and tactile sensing, I see it at two different branch, not compete to each other. But I mean, soft robotic is more than the robot-centric kind of thing, and sensing is like more objects or world-centric type of things. So in my work, I use soft hand to do grasping. So for soft hand, for sure, if you have rigid objects and simple tasks like pick and place, maximizing the chance, soft hand would give you advantages because it's soft, it conforms to the surface, creating more contact area, maximizing the chance. And but in the case of more manipulation complex tasks, I don't think now I've seen any soft hand that is able to, let's say, control the deformation of a cable or a piece of cloth or a sponge even. So and this work, the main idea is having the soft robot equipped with different sensor. Is it enough to grasp a deformable objects because it's soft, right? So you don't crush it. That's the hypothesis. But in the end, when I applied more and more forces, the objects still crush. So there, again, highlight for the importance of sensing objects deformability and then choosing how much force you want to apply. So that's the place of my work. And in my opinion, about the two community, it would really go down to the road that what are the application you're trying to aim for. I mean, for manipulation tasks, I would lean more on the tactiles because it gives you better sensing and better control of what is happening in your hand. For the soft robotics, again, it's deformable object itself, so it's really hard to control the deformable, control the hand to a specific configuration you want. And I mean, is the deformable itself is already a complex. So, well, even though you have simple controllers, to actually control it to a desired configuration is actually a very complex task. And I mean, again, it really comes down to the applications you want to aim for and choosing between the two directions.
Okay, so when you said in the beginning that you consider them orthogonal, you really are referring to the fact that one is good for something, the other one is good for something else.
I mean, in my opinion, I see it that way, at least.
Okay. Because something that I found very interesting about your work was that in some way you were combining both of them. And I personally think that I actually think that this is the right direction, in the sense that actually providing tactile sensing to soft robots might be a way to also give the capability of being able to control states that in this moment are uncontrollable, because you are entirely relying on the sort of intelligent design of the hardware. And on the other side, some of the advantage of the soft robotics could be applied to the domain of tactile sensing, which is typically hard, non-deformable hardware, where even just having a little bit of more compliance might actually be beneficial to have some of the benefits.
It might be the fact that I moved away from soft robotic for too long, and I kept my thought about soft robotic back then with the very simple and naive hardware. So I don't know what is state of the art of it now. So that's why I lean more about the sensing, because I do more sensing and planning. But I agree that, I mean, if now you have a really good model of soft robotic hand, for example, the compliance will give you many more advantages. Like the compliance itself is safe. offer safe interaction with human and objects, and also, I mean, providing more contact area in scene is conformed to the objects, something like that. So I mean, I agree that combining them would create something beneficial, especially show in my work that you need both of the aspect.
And that you are, through your thesis, you are actually able to now understand better the deformability also, soft robots and be able to control it. I think that might be a very interesting potential future contribution. Now, I think so. I guess going toward now, I'm done with the sort of low level nitty-gritty details, but I still would like you to answer a few questions about now the more general and sort of the future of the community. So I would be very interested in knowing your opinion, given all of your very interesting work that tries to go toward generalizing to objects, more in the wild, I would say. But all of these works are still somewhat constrained to very artificial environment, lab environment with a single object on a table. Can you tell me more about what do you think that we need before we are able to achieve, manipulation and grasping capability to really in the wild? When we will have robots that are able to clean our kitchen, and what are the components that we are missing?
Okay, interesting question, of course. Okay, so you are right that all of my work here is dealing with single objects, and most of them are open loop. That is the strong point I want to make here. So one of the future direction I personally want to go, or I think it is important, is to have a closed loop control or a closed loop policy, whatever it is called, so that the robot is able to correct itself if it's understand that it's making errors. For example, now if you want to, let's say, folding cloth, for example, so you fold, you're doing somewhere wrong, you correct yourself. That's what we do, human do. The same thing apply for putting dishes in the kitchen or in the washing, in the dishwashing machine. Yeah. So I mean, perception is one thing. Planning is the other thing. But I mean, now what I can think of is to have a closed loop, like control, where you can actually know you are making mistake and you try to correct it. Like unlike the open loop work nowadays we have. That's something important. And for closed loop, you face difficult challenges like how fast your perception work, and how fast are you replanning your stuff. So that's something I can think of at the moment. And maybe also a side note is since nowadays we train stuff in simulations, there is sim to real gap as well. So I mean, this sim to real gap is something has been addressed for decades, I think, and it's still there. So I think sim to real and closed loop is the potential direction for the future, in my opinion, of course.
Sim to real, I would argue that we have seen pretty impressive improvement in the last few years, with some fairly convincing.
But well, true. I'm talking about in the aspect of deformable objects as well. So like granular materials or cloth or anything you're trying to simulate in simulation. One reason is that the simulators for deformable objects is new, so you don't expect to have a perfect model of it, and it's really different. I mean, nowadays in a couple of years there are tons of simulators just for simulating granular materials, and you have a lot of tasks in the real world, like pouring water or something. So I'm talking sim to real in that context. So At least that's what I'm seeing when I read a couple of papers recently.
Maybe one thought here is that some of the advances in sim-to-real seem to come not so much from having better simulators, but rather from having better algorithms. So perhaps one potential way of approaching this would not be so much as to improve soft body simulator, but rather having better algorithms that can deal perhaps even with rigid body simulators, but can then generalize soft objects. And in some of our own work, in hand rotation and grasping, we do seem to see some evidence that this might actually be possible.
I mean, we've seen like domain randomizations working pretty good to solve that problems, right? And I mean, I'm not saying we should having better simulator. I mean, if we have, it's nice. But having more complex algorithm, like nowadays people use differential model to update whatever you have in sim from the real world data. So that's one way to express the gap. So I'm not saying we should have like really accurate simulator, but having like go into that direction to reduce a little bit the gap is better. But I agree with you that we need more complex algorithms.
And so then what you're proposing would require fully differentiable simulators. So something like Isaac Dream would be out of the question.
I mean, that's one of the options. I mean, just one of the options I've read.
I'm genuinely interested in knowing,
Yeah.
what do you think is possible, or what do you think is the future?
I mean, that's one of the direction I can think of. Yeah.
You said a few minutes ago something that was very interesting, which sort of need another question. About closing the loop. In this experiment that you have with the sponge with scraping, which by the way was very impressive. I really liked it. I think it was an excellent demonstration. But it doesn't quite seem that you close the loop. And you already said this in your own dissertation and in your work, that you basically don't really have way of updating in real time informations about sort of the state of the environment. So my question is whether it could be possible in some future work, perhaps to address this by using tactile sensors that are able to perhaps infer in real time what are the actual contact forces between the sponge and the object. Have you already given some thought of this?
So when I did that sponge work, I have so much time to think about its limitations, and like as I wrote in thesis, that not able to have the real time feedback from the real world really, I mean, is a problem. I mean, to close the loop, you need that. And to be honest, I didn't have any idea how to do it, because you basically have a sponge here and an object, and you operate here, so you have the occlusion from the vision and whatnot. So I couldn't think of a way to obtain that data purely with vision. Maybe with tactile, you can have some sort of spatial representation or something to I mean, not exactly the contact area, but I mean some information about what's happening inside. And that exactly why I think haptic or haptics is complementary for vision, because for some tasks you are totally occluded, you don't see anything, and you need some kind of information there which complementary for each other.
Yeah. As a human, it would seem that if you had, if you were passing a sponge, you are to some degree able to detect or predict where the sponge is in contact and compensate accordingly.
The thing is, I can't really deduct where we have that intuition. Is it because we feel something in the risk, or is it because we have the knowledge about the object itself? So I can't really come up with the intuition where the human, I mean, obtain that information. But of course, in that case, vision is totally occluded. So for robots, maybe having some kind of feeling in the wrist or in the end effector would help.
This seems like a splendid ablation study to perform and a great paper to write.
Thanks for that.
To conclude, going back sort of to this, goal of being able to manipulate and interact with general purpose, objects. Can you sort of again summarize for me and for the audience, what is the impact of your work that you have done in your thesis, and what do you think are the necessary next steps that where this work can be expanded?
So I mean, for state-of-the-art method or current method, existing work only usually do it in the way that you recognize the object, and then you do something with it. With my thesis, we hope that we can provide the robot with some basic or deeper understanding about the objects, like frictions or deformability, so the robot have more awareness of what it is interacting with, and then you can use that knowledge to do the planning. So I would say all of my work is based from a human intuition, where you look at an object and with the past knowledge about the object, you know if it's deformable and whatnot, and you already plan something in your head while thinking about that. So I want to give the robot that capabilities, and it is demonstrate that it definitely helpful, can increase the performance and task performance. And in the future, again, one of the limitation here is open loop, so plan and act. So one of the future direction I would go for is to have a robot that have the understanding of the objects, but can also adapt to its mistake. So if you, so it's the closed loops control, where you try to do something and you fail, and you plan again, having the same knowledge in mind, and try to correct yourself. I think that would give the robot more capability to be in the wild 20 or 25 years or so, hopefully.
Just a good timeline. Thank you very much for your answer and your time. I do not have any other questions. Okay. Okay. So to summarize my thoughts regarding the thesis of Mr. Lee, I believe that the topic that his thesis deal with is an important topic. It's a very timely contribution in the wider scientific scenario, community, and topics that other people have been dealing with. And indeed, there are not so many works out there that are currently doing this with the quality that Tran actually does. In particularly, I've been very impressed with the good intuition of really embracing the deformability of objects, which is something that people are, most people, both in science and in industry, are actively trying to avoid, where people want to avoid deformability. And instead, I strongly believe that embracing it will be the future, and that we need more research in this. Overall, the thesis demonstrated an excellent scientific production, published in excellent venues that are well recognized by the community. And the presentation that he provided today is clear and accessible to the audience, and at the same time highlight, both in the maybe a bit more in the thesis than in the presentation, but it presents very well-defined scientific questions, and the answers are convincing, are thorough, and are well presented. And so I'm happy to accept the thesis, to accept the thesis of Tran Lee.
Thanks. Now would be the time for the audience to ask the question if someone has any question.
If there are no questions from the audience, so I want to thank you everybody for participation. I want to especially thank Roberto Calandra for being so potent, and I declare the defense closed. There will be coffee and cake served just outside this room, and there's also possibility to congratulate Tran outside. Examination.
Thanks a lot. Yeah.
I'm bring these. I think it's best if you bring these. I can take this. Yes. I can water as well there, but yeah, please.
Mai hỏi Toàn đọc xong chưa rồi, thì mai đi hỏi cho anh đọc. Áo luôn cái này. Nhưng mà số lượng này chợ nên thì người ta dặn là phải mặc ấm cho thoa không bị phết. Thảo cái này của em là chỉ là một bông hồng thôi. Có được không? Có sao đâu. Nếu như thì lắm trên hả? Để áo đây đúng không? Tới đây, chuyển tới đây mình đồ đẹp lắm. Không có cho mình. Nếu gỡ cái đó nha, đừng nói là cái bệnh gì. Gỡ luôn hả? Thôi chị ơi đừng gỡ chị ơi. Mình gỡ cái này thôi này. Đó. Cái này ra còn không được xoay vòng. Sao sẽ nghĩ chọn? Một. Tôi nói nó bỏ nhiều rồi bỏ hết nha. Nó siêu nở luôn đó. Em cũng nhớ là chị chốt cái câu điện thoại. Gì đây? Cọc lên liền. Ủa bạn ơi. Này là option 2 này. Cha luôn không? Người có không có người xạo đâu. Hả? Người quá.
I can do it.
Okay.
I have to clean this stuff. So.
Right.